Welcome to another exciting lecture, Lecture 11, Information Retrieval in the winter semester 2015, now 2016. I will say something about exercise sheet number 10, which was naive Bayes. You liked it. And then contents of today is we talk more about classification because it's so important. We'll talk about linear classifiers, which is a generalization of what we did so far. Then I will prove or begin to prove that naive Bayes is in fact a linear classifier, which was not obvious from what we did in the last lecture. And you will complete the proof in the exercise sheet. Then we will talk about perceptrons, artificial intelligence, Terminator, and then support vector machines, which are the better perceptrons, but only very briefly. Your exercise sheet will be to complete the proof and to implement a perceptron. It's very nice and very simple, very little code, but you have to understand it and compare it to naive Bayes. We will talk more about it in the end. First, about exercise sheet number 10, naive Bayes. Many of you, everybody basically liked it according to what you wrote. Linear algebra, you're starting to like it, love it, was surprisingly useful, so some initial resistance now overcome. Surprised how fast and simple the LA solution was, exactly, yeah, if you didn't use the boring and inefficient for loops. You make use of this power of matrix multiplication, it's also fast, even in Python. So people are, if you are struggling, it's not really linear algebra anymore, which is nice, but the libraries, or to put it this way, that's what somebody wrote. Yeah, maybe they are hard to get used to. Yeah, there are some, you have to get used to it as always, but then it's great. Yeah, somebody wrote all the code on his own because easier that way. Surprising, but yeah, for some people it's just easier to start from scratch. Then we prepared quite a bit, right? Reading the matrices and stuff, but that's fine too. Okay, about the results, let me just take solutions from one of you and let me show it to you. So this is yeah, let me first look at the files again. So let's look at the genres. So this was the training set, right? You had a lot of movie description. We looked at it in the last lecture already. Alien, love triangle, blah, blah, blah. This was science fiction, comedy, thriller, animation, and documentary. So 5 classes. So you have something to train, to learn from. So that those were 70,000 pairs to learn from. And then you have the test set, of course, with other movies, where you don't know the label, it's just given here so that you can evaluate whether it's correct or not, and then, yeah. And so let's just see what happens if we run naive Bayes. So this is one of your solutions on, yeah, so train is the first argument, test set is the second argument. It's 100,000 movies, right? So it takes some time, and then see something like this. So those were typical values which many of you reached. So it's, right, this is 65% precision, which means of 65% of the times where the algorithm said it's a thriller, it's really a thriller, right? And of all the thrillers, which are really thrillers, 63% were found. So you see that precision and recall are very similar. You also see that some classes work better than others. Documentary worked best, right? And science fiction worked worse. So for some reason it was harder to predict this from the words. Then another thing that, yeah, most of you saw, I guess, is when you look at the words, then you get a lot of frequent words, right? Let me just summarize this on the slides before I go back to this and show some more. So this was the overall precision. It's like 73. It's not bad. It's not great, but it's surprising that it works so well, right? You're predicting something like the genre just from words, without any understanding of the words, just from statistics. So it's not bad. On ratings was a bit worse. Worked well for some classes, not so well for others. Let's maybe also look at the results for the ratings. I haven't tried it here, but I guess it will work. So the ratings were 4 ratings, right? R which is all the interesting movies. G is general audience, and then PG, parental guidance, and parental guidance 13. So what do we get there? This should be faster because it's a smaller set. So G, general audience, works very well, very well. So again, you have these words which don't say much. Then you have Japanese, which is surprising. Most of you got that. For some reason, all the yeah. This is interesting to figure out what happened. It's probably because most of the Japanese movies are of the kind that they are for a general audience, at least in this set. PG and PG-13 are harder, lower numbers, which makes sense, right? Because it's hard to distinguish just from the words whether you need to be 13 or 6. I think PG is, yeah, starting from 6. And R is again easier, yeah? And again, you have these words, yeah? So G rating worked super well, documentary worked well, not so well science fiction, PG-13. Yeah, this we already saw. Words with the largest probabilities were mostly stop words. You call them stop words when they don't mean a lot. You had some, like comedy is usually indicative of comedy. But for the R, I don't know if it's the case here too. Yeah, you have to go really far down in the list to find something which has something to do with R, like horror, thriller. Yeah, R-rated, which is indicative of this. If you think about it, they don't really hurt because they are in everywhere, right? So you might think, oh, naive Bayes is so stupid, it doesn't work, I should eliminate them. But everybody, every class has the as the most indicative word, and then it doesn't matter because you're just looking at which gets the highest score. So if all of them have the, film, and it doesn't matter because it's only about relative probabilities. So here in this solution, we actually have I think I had it somewhere already. There's an option, ignore common words. So if we do that on the genres now again, you can just remove the common words, right? With a list, or just remove the most frequent ones. I said it on the slides. And let's see what happens. So now you get more meaningful words, right? If you look at science fiction here, now directed as, still some stop words here, and then science fiction, they come number 3 and number 4. But the numbers are not much better, right? So it's interesting. That was part of the exercise. It's always part of our exercises. You do some improvements, you have a great idea, oh, I remove all those stop words. Doesn't really become better, right? There's also an option here, use pairs. I also, yeah, instead of just words, you look at word pairs. Let's see how well that works. Also, yeah, bigrams of words, all phrases. Let's see what happens. Yeah, why does it take longer? Because there are more pairs. So now you get something like this, right? So this is just sequences of words following each other. And still, interesting words. So thriller, you have Hong Kong here as a phrase, which is pretty high up in the list. Crime thriller, drama written, makes sense, right? This is, you look at all sequences of 2 words as features. But the results are, yeah, it was 89 before, now it's 90%, yeah? So that's quite typical also for this kind of research. You have ideas, looks like a great idea, and then you're disappointed by, sometimes gets even worse. Yeah, that's what I wanted to show you. Which precision is considered good? That's another interesting question here. I have one slide on it. So is this good or bad? 90%? What should I expect? So what's the baseline? So the simplest baseline you probably think of immediately. When you have 5 classes, it's just you guess. You always guess one of them, right? Then what's the precision? It's 20% for genres where you have 5 classes, right? You get it right with probability 1/5. For ratings, you get it right with probability 1/4. So it looks like that's the baseline, but that's wrong. It's very important to understand this. Yeah, that's just the probability to get it right is this. You just always, that's a better baseline. Pick the most frequent one in the training set, right? 41% of the movies are comedies, yeah? So you always say comedy, then you get 41%. because you get all the comedies right. If you have a set where 90% are of a particular type, say 90% of the movies in your set are a comedy, and you always say comedy, you get 90% correct. So that's, you always have to compare to that baseline. And that's actually pretty frequent that you have a skewed distribution. So works really well when one class is very frequent. Here it's not very, but somewhat. You might also wonder whether that's a good baseline. You know the distribution in the training set. I have so many percent this and so many percent this. So maybe I just pick with probability according to the relative frequency in the training set, but this is not better than baseline 2. And generally worse. I leave it to you. It's a nice exercise. This is a little question which you might also get in the exam, right? Why is this not better? You have to think about it too. It's 1 line of 2 lines of math. So why is this not better than this? I won't answer it now. It's something for you to think about. Any questions about the exercise sheet? We will talk more about naive Bayes now. But first, linear classifiers. So, what are linear classifiers? That's now a bit more general, so it's again about classification. Classification is important. Again, we have had it now for several times. Objects are just vectors in d dimensions, where typically d is the vocabulary for us, right? For every possible word, you have 1 dimension, and then you have the 1 or 0 there, whether it's there or not, or the count, or even TF, IDF, whatever, right? Now, for now, only 2 classes, and we typically call them +1 and -1, or just plus and minus, yeah? And I would say in a second how you can generalize from there to more classes. Now what a linear classifier does is you try to separate the points. Now think of it geometrically. So if you are in 2 dimensions, it's just separate them by a straight line. Yeah? So let me just draw a picture here. Now Frank just left, so let's hope it works anyway. So maybe I have all the pluses here. Yeah, I just write plus in 2D, and I have all the minuses here. Yeah? And now I have to find a linear separator, so that's an example in 2D. Then I might choose this line, yeah? And so if it's here, I think it's the touch on off. Touch off, that was the right thing. If I put my hand on it. So now here on this side it's plus, and on this side it's minus, right? That's the so if that's how linear classification works in 2D. So if I have a point here, yeah, what is it? It's a plus because it's on that side of the orange line, right? And now you can think of the same thing in higher dimension. If you have 3 dimensions, it's a plane which just separates the space in 2 halves. In 4 dimension, it becomes hard to imagine. Yeah, but you can do the math, of course. That's a linear classification. So, and of course, yeah, it might also be that you have a plus here, and then you can still do it, right? It's just that you get it wrong for some. You don't, yeah. It does not have to look like this. We'll talk about this in a second too. So hyperplanes. So now it's more linear algebra, which you love by now. So we need to define this thing here. This is crucial for all this learning classification work. You always have lines in 2Ds or hyperplanes in higher dimensions. So we need to define them. So some basic linear algebra again, which is very nice though. How do you define a hyperplane? Think of a line or a plane in 3D, and the rest is just generalization. So here are 2 very common definitions. They are equivalent, and I will prove it so that we get used to some LA math again. This is the definition by anchor point and basis. Let me just draw a picture to, yeah, so one way, so you have a plane here, so that's now 3D, yeah? And one way to do it is you have one point on the plane, and then you have a basis here, right? This is maybe my H1 and this is my H2. That's definition 1, right? So I have a point and a basis, and this defines the plane for me. So here I have it. So it's an anchor point A and the basis, which is, of course, if it's in 3D, the basis of my plane has 2 dimensions, right? And then my hyperplane is just defined by all the points A plus any linear combination of these two, right? With a linear combination of vectors from a basis, I get everything in the span. I think this should at least ring. Yeah, you should have heard this somewhere at some point. The definition 2 is by, so this is a little complicated because you need a lot of variables, right? You need d minus 1 vectors and another vector. Here's a nicer definition, which is the one which is usually used. It's you have a normal vector. So let me draw this in. Yeah, it's this. This is the vector, and it's usually called W. Now this is very confusing because we use W for words. So in this lecture, W is the normal vector. And it's called like this because it's usually weights. And that's why this is just, when you look everywhere, it's a W. And the B, that's now a real number, and you can't draw it in here because it's just some number. Yeah? And now the hyperplane consists of all the points where the dot product with the normal vector is some fixed amount. Now that's not so clear that this also defines a hyperplane, right? So let's just prove this. And I think it's interesting to prove it. It's a short proof, but it's interesting. This definition is clear, but it's a bit clumsy because it involves so many vectors. This just involves one vector and one real number, and it's the same. And it's W is the normal vector. So for the proof, so we have to prove if you have this definition, you get this one. If you have this one, you can get to this one. I use one basic thing from linear algebra, which I don't prove. And also it's here so the real numbers, this is one convention to have this in bold. If you have any questions, you ask it, right? If you have some vectors in d-dimensional space which are already orthogonal, like in 3D you have 2 vectors, right? Then you can always find a third one which is orthogonal to all of those. Or more general, if you are in t dimensions, just imagine 10 dimensions for a second, and you already have 4 vectors in 10 dimensions which are orthogonal, then you can find 6 others such that all of them are orthogonal, right? So it's basis completion. Okay, now let's do the 2 directions, that the 2 definitions are equivalent. So assume x can be written as a plus sum, let me do it slowly for now, hi, right? Yeah, so this is a point by definition 1, right? It's just the anchor point plus some linear combinations of those, right? Now pick W orthogonal to the H1, H d minus 1, right? Which I can do because there are d dimensions. So according to this basis completion, I can find, and this will be the normal vector of the plane, right? Now let's just look what happens when I take this times this, and this is always the dot product between vectors, right? Then I get W times A plus, and now, of course, the same laws of distributivity and everything, they also apply here. So linear algebra is really nice, right? Because if you can prove something, it always works out so nicely. This one thing you should really understand about linear algebra: if you have vectors which are orthogonal to each other, right? Then So if a vector is orthogonal, then the dot product is 0, right? Actually, it's equivalent. And the dot product is something which we can just compute, right? It's the sum of the component-wise products. In this thing here, we just define it as our B, which is the dot product of the W with the A, and then this is B, right? So, yeah, if you have something, a point like this, then it's then this is satisfied. Let's also do the other direction. Let's assume we have Wx is equal to B. Now now we have W's given. Now pick H1, some basis of the rest of the space, such that W, such that they are all pairwise orthogonal, right? Orthogonal, that's the sign. So now I have a basis of my d-dimensional space, which means I can write a vector x as, so it's the most basic things from linear algebra. I can write a vector x as a linear combination of those alpha I times hi plus some alpha d times those, right? So I can write any vector from d dimension as a linear combination of those. So now let me just take the multiply this with w. So now I get I1 d minus 1 alpha I times w. This is now the dot product, ai plus alpha d of, and this is equal to b, right? Now this here is 0 because they are orthogonal, right? And this here is, well, that's the norm squared, right? Dot product of a vector with itself is just this is also one basic thing which we used many times already. That's just the sum of the xi, the component squared, right? Obviously. So x is, yeah, if you write x like this, let's say, yeah, d dimensions here, it's just the sum of the, and this is just the norm of the vector squared, yeah? Norm is just sum of the component squared, square root of it. Okay, so we have so we have alpha d times w squared is equal to b. Let me just multiply this by w on both sides. I get this times w is v times b. So what do I want to write here? Okay, and then I have alpha d times w is just wb divided by squared, and I just define this as my anchor point, right? And then I have, if I have this, then I can just write this as like here. Okay, end of proof. Plus a. Any questions about this proof? I think you have to look at it yourself at home. But the basic steps, yeah, we just used three things. You can write thing as a linear combination of vectors from a basis. Dot product of orthogonal vector is 0, and some trivial things. I think I will just continue. That's important. The distance of a point from a hyperplane, not only the distance, but we need to know all the time. So we have a line given according to the definition. And this is now what you also need for the code. And I have a point, and now I have to figure out, which means calculate, is my point to the right or is it to the left? And maybe also how far is it to the right and how far is it to the left? Yeah? Now here you can see it or just measure it with a ruler. How do you compute it when the two things are vectors in d dimensions, right? And for that we need the proof we just had and something else. It's actually again quite easy. So let's take this definition. This is the nicer definition. A hyperplane is defined by the normal vector and some b. Yeah? And then it happens to be that the distance of a point, any point x to the hyperplane, is just, you just take this minus b, and then you just see whether it's positive or negative. Then you know the side, and if you want to know the distance, you just do this. Let's just prove this. And this is what you need in your code, right? So it's actually very easy. If you just want to know the side, you just compute, you have this vector which defines the hyperplane, you dot product, again, very simple, with your object, minus some offset, and now you just look positive or negative to know which class. That's it. Yeah? So you do the algebra once, and then it's a super simple computation. And that's the computation you will have in your code 1,000,000 times, and it's fast, and that's why these things are quite practical. Let's just prove this. It's a very nice proof. I like it very much. So I think I will just prove it for one side, and then you can do it for the other side yourself. So let's just, so this is my W. So let me also consider W0, which is just the normal version of this. So W0 is just W divided by the length of W, which means W0 has length 1, right? It's just a unit vector in the same direction. So which means everything in this direction is plus, right? So let's look at a point x now here. Yeah, this is a point x. How do we find out the distance? So this is how we measure distance, right? Let's say this is distance r. Let me call this point x prime. Now I want to compute the r. How do I compute the r? Now some beautiful linear algebra again. It's not so easy to draw. Yeah, this is the r. Is this readable? So, well, I have to write and somehow relate these things with the variables I have here. So I can write x as, well, it's this x prime, which is on the hyperplane, on the straight line in this case, plus r times the normal vector, right? Which is just one unit in that direction, right? This is because this is orthogonal here, right? So that's certainly true. So, because that is so, let me just multiply this with x now, which is, so this is wx prime plus r times w times w0. And this is b, right? Because it's on the... no, that's not b. That's wrong, I'm sorry. Let's... no, wait. So this is... this is b, right? Because x prime is on my straight line, right? And my straight line is just defined by all points where this dot product is b. And this I can also simplify. This is just, well, w is w is just the unit vector times its length. And so I have unit vector times unit vector is just the length of the unit vector, which is 1. And so this is just R times W, right? Times, well, I can just write it like this, and this is 1. Yeah? Which means Wx is B plus R times W. And you see we almost have it, right? And now I can just resolve for the R. So R is just W times, so this is always the dot product here. Yeah, whenever it's between two vectors, I don't have to write it so explicitly, but maybe it's helpful. Minus B divided by W. Yeah? So, so this was the case 1. Forgot to write this, yeah? Maybe I write it in a different color when X was on the right side of W, right? Case 1. This was case 1. X on right side of H. And for the other case, well, I'm sorry, for the other case, you can, it's just the same. Now it's just I have minus here, right? Because the vector is now going in the other direction. For the other case, we have X equal X prime minus R times W0. And then when we do the same math, you will get R equals to minus W X minus B times W. End of proof, right? So that's it. Even if you didn't fully understand the proof, it's very important to remember this, because that's what you need in the implementation, yeah, to find out on which side this lies. You just, and this is not, well, without doing the math, this is not something you could just come up with. Compute the dot product, subtract this B, and then you look at the sign. That's it, super simple. Okay, now before we go to concrete classifiers, this was just linear classification, which means just two classes. Is it on this side or on that side? And it's again two classes in 3 dimensions. You have a plane, is it on this side or on that side? How do I generalize this to more classes? It's not so obvious. Well, you don't do it directly. This is one common option. You just build K classifiers now, right? For example, think of the movie genres. Now I just have one for comedy, which just classifies, is it comedy or not comedy? Yeah? One classifier which just does this. Then you have one classifier, thriller or not thriller, animation or not animation, science fiction or not science fiction. So you have 5, yeah? If you have 5 classes. Now, of course, you have the problem that maybe the comedy versus non-comedy classifier says comedy and the thriller versus non-thriller. And now you have to pick maybe by the stronger signal. Voting is, I think, not quite the correct word, but I guess you know what I mean. Yeah, when 2 classifiers shout it's me, then you have to take the one which gives the stronger probability. Or you just compare all of them. You do comedy versus thriller, thriller versus science fiction versus animation, all pairs. Yeah, problem, that's a lot of classifiers. Yeah, so if you have 5 classes, it's 5 times 4 over 2, which is 10. Still reasonable for 50. Yeah, but already 10 classifiers, right? So that's one way to do it. Or you try to, maybe you do the theory and then you see, oh, I can generalize this to do more than 2 classes directly, right? We will see in a second that naive Bayes is a linear classifier, and naive Bayes, just by the way it works, also works for more classes. I did all the derivations for arbitrary number of classes, right? So for naive Bayes, it's not restricted to 2 classes. For the exercise sheet, you will just do this. And actually, we already did all the preparations for you because we are so nice. So it's just, here you did comedy versus thriller, okay. So here it's not comedy versus not comedy, but 2 classes. And here it's R versus not R, right? So you just have, yeah. So in any case, it's just 2 class classification for the exercise sheet. What about when the data is not linearly separable? Yeah, what do you do then? That will be the typical case, right? Well, one is you extend your method to accept outliers somehow. Now, naive Bayes, you don't know yet that it's a linear classifier, but it does this by definition. It always finds some separation. Right? You don't know yet that it's a hyperplane, but it always finds one, whether this is a good hyperplane or not. Yeah, you can just find one, and then you predict everything on this side is minus, everything on that side, whether it's good or not. You can do it. Or let me just do this. I just want to show this to you because it's so simple. And just assume you have points in 1D. So this is points in 1D, and let's assume I have, so this is 0 here, and here I have maybe, so this is 1, this is 2, this is minus 1, this is minus 2. So here I have a point x1, which is minus 2. Here I have a point x2, which is minus 1. And here I have a point x3, which is 1. And here I have a point x4, which is 2, right? And now let me assume that my class labels are, this is a plus, this is a minus, this is a minus, and this is a plus, right? Now, linear separation in 1D would be one number, right? Everything greater is this class. Now I can't separate them, right? Impossible. Well, now I can just lift these problems to 2D. I can just do, so here I have x. And this can be, there's a whole theory about this. So instead of x, I just take x comma x squared, for example. So now this point here becomes this point now. So it's now just point 1, 1. This point here becomes 2, 4 in 2D, right? This point here becomes minus 1, 1, right? So I just, out of just a transformation, every point is transformed to this, the original coordinate and the coordinate squared, and now I get a point minus 2, 4, right? And now let me just, the classes remain, so this is a plus, and this is a plus, and this is a minus, and this is a minus, et voila, now I can separate them, right? Interesting, huh? This is just to show you, let me, yeah. Now I have a, yeah, now I'm in 2D. Now a separator is a 1D line. I could not separate them in 1D, no way. Just by lifting it to a higher dimension, I have more possibilities, and now I have a separator, yeah, many separators, in fact. And that's a super important trick in practice. We don't do it in the exercise sheet, but just so that you understand that linear classification, which might seem too simplistic, is actually quite good, because you just go to a higher space and then it might work. Any questions so far? Okay, now 3 parts. 3 more parts. First is naive Bayes. I will start something, you complete it for the exercise sheet. Naive Bayes is actually a linear classifier. We didn't introduce it like this, and it's interesting that it is. So just some recap. So what were our features? It was just all the words from our vocabulary, and I will now call them V. This is very important because now W is the normal vectors for hyperplanes. I could just have chosen a different names for these vectors, but you read any literature, papers, textbooks, Wikipedia, this normal vector in the context of classification or learning will always be called W. So I also call it W here. So I can't use W for the words. So I will just use V for the words here. Yeah? V for vocabulary. I think that's, I thought 1 hour about this, how to resolve this. In the last lecture, last time I gave it, I just didn't resolve it. I just used W for everything, which was a bit confusing. So now W is the vector from the hyperplane. Maybe I will just draw it again, right? So this is W. Yeah? So now it's clear. So this is what naive Bayes did to predict, is this the right class for this document? You just multiply all these probabilities. I now write them a little bit differently, right? Because there is no V here. So it's just I have my 1,000 words, and now for every word I have the probability for that word in that class. So here I just use an index now, not a W, right? So I go over all the words in the document, I sum up all these probabilities. That's what you did, either in boring for loop or with matrix multiplication. Multiply it with the probability for the class, how often it is there, divided by this, and this I don't need for relative comparison because it's class independent. Yeah? And this here, if I have a word like film 3 times, I have this probability film for this class 3 times, right? Which means I can also write it like this, right? I just go over all the words in my vocabulary, and I now have this factor for a particular word. So this may be the probability for film in the class to the 3. If film is there 3 times, I have this probability p to the 3. If it's there 0 times, this factor is 1, right? So it's also fine. I can actually iterate over all the words. And then times this, right? Where this is just number of occurrences. This is what we had already. Now, I claim, and this is what you will prove in the exercise sheet, looks frightening, but it's actually super easy and it's fun to prove. You just have to write it down and then it works out magically. So it's actually a very deeply satisfying thing. Yeah? Especially if you're afraid at first, it's even more satisfying. You write it down and it just comes out the right thing. Yeah? I just define my W, which is the normal vector, as follows. It has 1 component per word. And the component for the ith word is just the quotient of these 2 probabilities and the logarithm of it. And the b, which is just an offset, a number, is just the quotient of the 2 class priors, 2 probabilities, logarithm of it, and the minus. And now this defines a hyperplane. And if you do prediction according to this hyperplane, it's exactly what naive Bayes does, right? Which means it says A, if this is greater 0, and otherwise B, and if it's equal to 0, it means same probabilities for both classes, right? Prove this in exercise 11.1, but just to help you a little bit and also for some more intuition, let's just do it for our toy example again, right? Yeah, and this is also great for understanding linear algebra and everything, right? It's really not hard, but you have to understand something. Let's just do this again. This is what we did last time. Let's just do it again to get in the mood again. So this is now from the training. So last time we had a slide where we predicted this for a fixed document, just to show you. Now I will do it for an arbitrary document, right? So we had this, the probability of class A and the probability of class B. So it's very easy now, this slide. Is this the probability of A for A was 2/3. The probability of B, the word B for class A. So this will again be our running example, was 1/3. And for the other class B, it was just the other way around. So it was just A was more rare and B was more frequent, right? 2/3. Now arbitrary, yeah. Now we have an arbitrary D with, yeah, what do we do? TF A times A. Yeah, TF is now just the number of times it, and let me just call it TFB times B, right? So what do we have then? Then we have the probability of class A, that the class is A, given that the document is D, is what? Well, it's just PAA over TFA, right? Times PBA over TFB. It's just from the previous slide, just by example, and I think this helps some people. Times PE divided by the probability of the document, which is just in the general case, so this is just 2/3 times how many A's I have, right? Now it's very easy to see. Times how many B's I have, time 1/2 divided by this probability, which I don't know. I could compute it, but I don't need it because it's the same for both. And I just need the relative number. And I can do the same thing for, let me just write it out because it's not so much work. TFA times, here it's just the probability for class B now, times PB divided by this D, and this is now 1/3 times 2/3. Now you see the difference. We already had this for times 1/2 divided by. Okay, and now let's just ask ourselves, when do we predict A? Well, the probability that C equals A is greater than the other probability. Well, that's easy now. And actually we can do, this is exactly the case when this is 1/2, it's the same, this is the same. So this will be exactly the case when 2/3 times TFA times 1/3 times TFB is greater than 1/3 times TFA times 2/3 times TFB, right? And this is, now it's very simple computation. I can just, the 2/3 I can bring to this side, so it's dividing by this, which means it's 2/3 TFA minus TFB greater than 1/3, and the same TFA minus TFB. Yeah, it's very simple math, and this is equivalent to, now I can just bring the whole thing here, which means it's 2 to the TFA minus TFB greater than 0. And this is, yeah, this just happens when the number of TFB is greater than 0, right? Which means if I have more A's than B's, you already guessed this correctly. And this is just prediction for a general document, right? You just do the math. It's relatively easy. You just have to do it and flow with it. And now let's draw this in 2D, right? So now I define, just remember those from what you will prove. So now I just wrote down let me just write down the two vectors here, right? And when you do the exercise, look at these two slides and compare the calculation and the geometry and try to understand this. This will help a lot. Let me just write this down now. So this is now, oh, wrong direction. So now I have a W is now equal to W1, W2. We are in 2D, right? Which means, and this is now log 2 of, this is PAA divided by PBA. This is what you have to prove. And this is log 2 PA class B divided by PB class B. Yeah? And this is, well, PA, this is 2/3 over 1/3, right? I can just write it here again. This was 2/3, and this was, it's good that I only have two letters, right? Otherwise, 1/3. So that was 2/3 over 1/3. It's 2 log 2 of 2 is 1, right? And the other thing was the other way around. It's 1/3, and this was 2/3, so it's 1/2. And log 2 of 1/2 is? What's log 2 of 1/2? You don't need a calculator. You look like you are listening, but maybe it's just a trick. What's log 2 of 1/2? -1, thank you. It's -1, yeah? 2 to the -1 is 1/2. And B is, that's minus log 2 of PA divided by PB, yeah? And PA and PB were the same in this example, both 1/2. So it's a log 2 of 1, which is 0, right? So now let's just write these as pairs, TFA, comma, TFB. Yeah, these can be now written as points in 2D. We're in 2D now. So this is the point 2A's, 1B, right? This is the point 5A's, 2B's. This is the point 3A's, 5B's. You tell me if I make a mistake. This is 3A's, 2B's. And this is 1A, 3B's. And this is 2A's, 4B's. Right? And now let me draw this here. Try to make a nice picture. So this is the number of A's. And this is the number of B's. And let me just 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now let me draw the, so my A ones are 2, 1. Where is 2, 1? That's here. That's my, let me first draw, that's 5, 2, that's here. Yeah, those are A. And this one is 3, 2, that's here. Yeah. This is A, this is A, and this is A. Now let me draw the 3 B's. This is 3, 5, which is here. Let me just draw it as a circle thing. Or let me also write it here. The other B is 1, 3, which is here. And the last one is 2, 4, which is here. Oh, not quite. This is B, right? Now what's my W? 1 minus 1. This is 1 to the, right? This is just this direction, 1 minus 1, right? This is my W. Goes 1 to the right and minus 1 in y direction, right? And b0, so this is, we just, this is my, and it goes in this direction, right? This is my w. And because b is 0, if you think about it, it means that it goes through the origin, right? Because if I have w times the 0 vector, and this is 0, it means it goes through the origin, right? So this is what naive Bayes will do in this case. This is the geometric interpretation. Yeah, and in this case, the data was linearly separable, and it actually found this thing here in the middle. Yeah, and this is what you have to prove in general, independent of a picture, independent of a dimension. Any questions about this? So I take it that you are just stunned from the beauty of all the algebra and pictures. I'm sure you are. Now we talk about perceptrons. I think the general idea was clear enough. The details you have to look at yourself anyway. What are perceptrons? Why do we talk about perceptrons? I will tell you in a second. They are really old, one of the oldest types of classifier. I mean, naive Bayes was this monk who was bored and that did some math. That was 300 years ago. That's beginning of last century. That's also linear classifier. Now naive Bayes comes from probability, and now we just proved or started to prove that it's all actually, you can also view it as a geometric thing by just defining your planes like this from the probabilities, and then it also has a geometric interpretation. Perceptron is linear right away. You try to compute the W and the B right away. And how do you do that? It's the simplest possible way to do it, and you will implement it. It's really simple to implement and quite interesting that it works. It's simple but tricky. And then you just iteratively improve them, a bit like k-means. You start with anything. Actually, we'll start with this all 0, stupid, totally stupid numbers, which don't make any sense. And then you improve a little bit. You always look at one of your training objects, and then you improve. And for some funny reason, which I will sketch a proof, this works. It's like k-means, whereas k-means was a bit more, this is even simpler but less intuitive that it works. With k-means, yeah, you were always centroids, assigned to nearest centroids, new centroids, assign. It some kind of made sense that this would do something meaningful. Here is less clear but easier. That's why it's a nice algorithm. So this is the algorithm. This is what you implement. It's even less code than naive Bayes. You start with the all 0 normal vector, which doesn't make any sense at all, and b equals to 0. You can start with anything, but start like this. So now you go over the objects from the training set in random order. Random order is not necessary if it's separable, but it has some nice properties. And now each training object after the other, right? You are now in training. Yeah? Understand what this means. Let's just to make this more, but we will look at an example again in a second. So now we have comedy versus thriller. So here we are, that's your data set. It's now 2 class, right? So it's, yeah, Bachelor Man is a romantic comedy, right? So you now have this. Yeah, this is a vector, of course. Yeah, documents are vectors. This is now so obvious for you. Yeah, that this is a vector, and now this should be comedy, right? And you go through them one after the other. So now you have your current W and B. You have your current hyperplane. Think of it as a straight line. Now you just see with that hyperplane, will it give the correct prediction on my next object? With my current hyperplane, will it say comedy or thriller? If it's correct, you do nothing. Yeah, fine. You just go to the next training. Yeah, you go over the training things again and again. If it's wrong, now you update. And the intuition, you see, it's so simple. You just try to intuitively push it in the right direction. So now it's wrong. Wrong means it can be wrong only in two ways. It's negative and should be positive, or it's positive and should be negative, right? Or a bit more generally, if it's in one class, I really want it to be positive and not only 0, right? So it's less or equal 0, and I want it to be positive. Then I do this change. I just add x to the weight vector and subtract 1 from b. If it's greater or equal 0, but should be negative, I subtract something from the x and add something to the, yeah. I hope you can see that this is what you have to do, right? So the code is like if, then, plus, yeah, so that's it. That's the algorithm. Yeah? And now you repeat. Yeah? One iteration here is always one, maybe I should write this. Yeah, I should write this. So fixed number of rounds. And you, yeah, again, it's the question, when do you terminate? But you're already pros now, so you find one yourself, right? So a round is 1 round, 1 pass over all training objects, right? This is a bit different from the previous algorithm. Just a second. In random order, you always change the order. This has advantages. I will talk about it later or maybe next time. Yeah, so you go over, maybe you have 1,000 training objects, you go over them, and then you go over them again and again and again, because it's an iterative thing, right? This is different from naive Bayes, where this wouldn't make sense. You compute something from the data once and you compute your probabilities. This is iterative, and this is actually what so this is the grandmother of all these deep learning things. They all work like this, right? You get your training objects, you start in some configuration, which is totally random, or maybe it's already something meaningful, and then you train the thing and it just sees the training things, yeah? It reads, it's like it's reading it again and again and tries to get better and better, yeah? And you do this, this is how they all work, even the complicated one. So yeah, you find out a good termination. Of course, if it doesn't change in one round at all, it will also not change in the next round, because that means everything is predicted correctly now. Yeah? You might not want to go that far, might be overfitting. You figure it out yourself. Or you just say, I do 10 rounds, then I stop. Just play around with it and look at the results. That's fun. So why does this work? This looks strange, at least to me it looks strange. I mean, it's simple, but it's strange. You add x to the weight vector, right? I think you should appreciate that this is strange. This is important. Yeah? This is the normal vector of your hyperplane, and you add x, which is an object. Why do you add an object to the, I find this strange. +1, -1, okay. But actually, if you, okay, appreciate it, let's look at the example. Let's just do a few iterations so that it's clear. It's just for fun. So let's start with w as 0, 0, and then b equals 0. And now I do, okay, I have to write the 2D things here again. This is 2, 1. This is 5, 2. Maybe not all of them. This is 3, 5. This is 3, 2. This is 1, 3. And this is 2, 4. I will only do it 3 iterations or so. So now I do, and this is my x1, and let me just go through them in that order here, right? As they are written here. x4, I think it always helps to see an example, just to settle any questions about the math. So now I just do w times x1 minus b, which is just 0, 0. Let's just do it very explicitly. 2, 1 minus 0, which is 0, right? Which means I do update. Yeah, when it's 0, I always update because 0 is undecided. Now I do 0, w gets, so what do I want it to be? It's an a, so I want a plus. Yeah, so it's an update towards a. So it's w plus x, which is now 2, 1. And b gets minus 1. Yeah? B is now b minus 1, which is minus 1. Yeah? So now I get next object. W x2 minus b is, so now my w is 2, 1, right? It's a bit strange that it's now the object from before. Now it's times 5, 2. And now it's minus b minus 1. It's plus 1, which means it's now 2 times 5 plus 1 times 2. It's 12 plus 1 is 13. Right? No change. 13 is greater than 0. I don't know if you knew that. No change. Yeah? Okay, next round. W times x3, right? The prediction is correct. It's greater than 0, and so W times x minus b greater 0 is class A, and W times x minus b less is b, right? This is how we also had it. So now one more round, then we are, so now it's 2, 1. And now it's 3.5, 3 and 5. And it's again plus 1. And this is 6 plus 5, 11 plus 1 is 12. It's greater 0, but it should be b, right? So now I correct it. So now I do an update in the other direction. Update towards b. Which means now I do the other thing. And I think it's useful, you get some intuition, right? This is too positive now. All numbers are positive, and it should be negative, because this thing should be classified as b. So somehow I need to make this, I need to get some negative numbers. So it makes sense to have a minus here. And you will see on the next slide why that is meaningful. So this is, so now it's the weight vector was 2, 1. And now I just subtract the 3, 5 ones, right? So it's a minus 1, minus 4, right? Now is that correct? Yeah, it's 2, 1 is my current one, and now I subtract 3, 5. So it's minus 1, minus 4. And the b, I just add 1. So this is now 0 again. And now, and so on. Yeah? You don't learn more if I do it further. Now, yeah, you get some. Now, this is now negative, so it now would probably work on this one. Or maybe not, but at least it does something meaningful. Now here's the intuition, and then a proof sketch. And then that's it. You can implement it. The point is, this is easy to understand, intuition. Somehow, here, the W and B are not good, because for this 3, 5, they're not predicting the right thing, right? It should be negative, but it's positive. So I have to correct them. This much is, and now I correct them in the right direction, right? So here, why is this the right direction? To add x or to subtract x? Assume this, yeah, in the other case, completely analogous. Wx minus b is negative when it should be positive. This is what we had in the first round. Now, I just update and it's negative and it should be positive, I add something, yeah? Here these are always positive and here I subtract something. Now what happens now? That's easy. Now just look at the new weights. Yeah? So this is now, yeah, I can write one intermediate step so that it's super clear. So this is now w plus x times x, right? So it's w times x plus x times x, right? So x times x, I already had it on the previous slide, is just the norm squared, right? Yeah, and minus b prime is just b minus 1, minus 1 is, yeah? So it's just what I had before the update, yeah? It's before update. This is what I had before, which was not right. It was negative and should have been positive. And this is greater 0, right? So the math, yeah, it was negative, should be positive, and now I'm adding something. So it's going in the right direction. It's not clear that it's enough, but recall that you're doing it in rounds. If you do this enough times, it will be corrected towards this. And in the other case, it's just completely the opposite. It's just the opposite. It's the same argument, right? It's positive, should be negative, and then I'm just subtracting something. So it's going in the right direction, right? This pushes in the right direction. Not necessarily enough, but I will repeat it. Now, the one thing that's not clear, and there's also, at least I didn't find it, no simple argument for this. You corrected for this object, now comes the next object. You corrected for that object. Maybe this correction destroys the previous correction. And that's the ingenious thing about perceptron. So it's not that it's trivial to come up with this, right? You always correct, that's why it's greedily in the right direction. Next object, it's wrong, I correct it. You always correct. And why? Maybe this goes on forever and you're just miscorrecting. Yeah? But this doesn't, it works. Eventually, if the things are separable, it will converge. Or you just stop after some rounds and then you will get something. The question is how good it is. It's your exercise. So here's a proof sketch. This does not give too much intuition. It's just if you are interested in the mathematics. First thing, this is a standard trick and it takes me 30 seconds to explain it. You can get rid of the b. The b just says whether this thing goes through the origin or not. I can just look at this. I just take a w, my original vector, and now here I take the b as 1. Yeah, so this is d dimensions. And this is one more dimension. And now if I take the dot product with a feature vector, and now I just add an additional feature, d plus 1, right? And I just put minus 1 here. For every object, I just have an additional feature. Now that's just a purely technical trick. I just have one more feature, which I always set to minus 1. Now compute this dot product. And this is just w times x minus b, right? So it's a very simple trick. And now you don't need a b anymore, right? I could write minus 0 here, right? I can just add this b thing as one additional component of my vector. And then that's also very nice, right? This is something not so intuitive about high dimension. You add one dimension more and you get rid of this, yeah? B is called the intercept term. Maybe let's just write this. Yeah, B is often called intercept in the context of learning term. That's not important. Just if you hear intercept when you read something about deep learning or whatever. Yeah, so actually I can omit the B, just put it, transform the thing one dimension higher. What you can prove, I won't do it very easily, is that your vector always increases by a fixed amount. That's the proof. If you like math, just do it. It's 2 lines each. It's trivial. and it's bounded by square root of k. Yeah, and this implies this. I can easily prove this implication, and I will just do this because it's so simple. This implies, yeah, if I have epsilon times k is less or equal c times square root of k, then I have epsilon squared k squared less or equal c squared times k, which means epsilon squared times k less or equal c squared, which means k is c squared times, yeah, I just get an lower bound. So if you prove these two things, if you come up with a better intuition why this works, I'm really interested. What you are doing, I mean, the best intuition I come up with is that you always correct the W, at least to some extent, in the right direction. Yeah? But this doesn't give you intuition. The intuition I was looking for is why don't these things cancel out? And here you have an argument from a completely different direction, right? That the length of the vector by one argument always makes an improvement, and by another argument it's bounded above by something sublinear in k, and this means that the number of corrections can't be arbitrarily high. Yeah, but that's just, if you're interested in the math, have a closer look. You don't need it for the implementation. Here are some problems with the perceptron, and then there's not much more. You will just implement it, play around with it, and compare results to naive Bayes. So if it's linearly separable, we just sketch the proof of this. It will find the hyperplane. It works. You can try it. Now, the problem with the perceptron is, let me just draw an example here. So assume my data looks like this. Plus, and here I have minus. Now here are some possible hyperplanes, right? Maybe that's one hyperplane. Yeah? This is an H1. Is this a good separator? Or maybe this is another one I could take. Yeah? This is another option, H2. Yeah? Or maybe this one, H3. Yeah? Should I take this hyperplane? Should I take this? If it's linearly separable, I have a number of choices, which is the right hyperplane. Yeah? Or maybe should I take this one here, right? H4. Somehow intuitively this looks more reasonable, right? Because it's somehow going more through the middle of those, right? This is really going close to those ones. If I would ask you intuitively what's the best separator, you would pick one which is in the middle, right? And the perceptron gives you it just finds any of these. And that's a problem in practice also, because it has no concept of finding a good one. So the main contents of today is hypothesis testing. So you want to test whether an effect is actually significant or just random. The exercise sheet will be to do that for the perceptron. For a simple baseline, we just talked about it. Simple baseline is just how I explained it in the last lecture, 10 iterations, that's it. And now you try to tweak it to make it better. And that's a very researchy setting, right? You start with something, now you try to make it better. And you try a million things, and now maybe it's 3% better. And now, is this really significant, or is it just because I was lucky, or because I tweaked it around so much? So here's now, for this exercise sheet, just a collection of things you can do to make the perceptron better. So this will be very quick. It's just for your reference. You can use it or leave it or think of other things. So those we already discussed. You can just play around with a number of iterations, maybe 20, 30, or 5. You can change your termination criteria and play around with it. Maybe when the change drops below a certain threshold or whatever. You can remove frequent words, you can use TF-IDF, or you don't have to do this, it's just inspiration to things which could be done. Yeah, use different features, additional features like word bigrams. We already discussed this. Here, for your curiosity, are 3 more things, and very quickly I will just show them to you. You can, yeah, some of you like this to try to tweak something, so I'm just giving a few more suggestions, not the contents of today's lecture. That's a very simple thing, averaging. You run this perceptron thing for here, maybe for 10 iterations, and you have 100 training samples, which means 1,000 times you check your W vector. Is it correct for this training sample? If not, you update it with the simple rules. Now, in the end, don't take the final W, just take the average of all the W's you have seen. Very quickly, why is this a good strategy? One intuition is, in the end, the W will separate your training samples pretty good. And there are just a few which are wrong. And now the final changes of W will just be to correct these last few predictions on the training set, right? And if you do averaging, you just de-emphasize these vectors from the end, which is a good idea. And also, if you have a value of W somewhere in the middle, which is really good for many training samples, then you will not change it for maybe 50 iterations, and you will have it 50 times in this averaging. So just one idea, averaging. Another idea, it's really another algorithm, logistic regression, but you can see it, and I like to see it as just a variant of a perceptron. It's very similar. Namely, this thing here, this is a function called the sigmoid function or the logistic function, to juggle around with stuff here again. So this is called the sigmoid function, and it's a, or sometimes also logistic function in the context of learning. Well, this W, so if I just have my Wx here, which is a real number, it can be minus 1,000, minus 5, then 0 is the point where it says, okay, I predict plus or I predict minus, and now I want to turn this into a probability. Now that's what, touch is still on. Then this is what this function does here, and it's, so here is 1, and here is 1/2, and this looks like this. Yeah? So that's what this function does. 1 divided by 1 plus e over minus t, right? It's just at 0, it's 1/2. The probability is 1/2. Below 0, it's below 1/2. Above 0, it's above 1/2. And it approaches 1 here and 0 there for large absolute values, right? So with this function, you can just turn this into the probability. What's the benefit? Now you can use maximum likelihood estimation to do some mathematics. I won't do it now. And this gives you, yeah, this is a more rigorous way of deriving these update steps. For simple perceptron, we just had, yeah, if this is the class and you mispredicted, just add x or subtract x, right? So here I should say this without loss of generality. B is 0, right? This was the trick from the incorporated into W. Yeah, you can incorporate the B into W. See lecture 12, see lecture 11. I don't have the slide now, but you will find it. If you just do the math, you derive at these steps, which are, I'm sorry, that's PowerPoint again, doing something annoying. Yeah, so very easy to implement. Sorry. Yeah, you just have these factors here, a and a prime, which is just a sigmoid function, which is just a multiplier in front of the x, and another factor alpha, which plays a role now, which is the learning rate. So even without understanding it, or maybe you want to understand it, try to do the math. You can just implement it and see how it works. Here's another simple trick, batching. In your simple, just a second. In your simple implementation, you did it element by element, right? And this was also inefficient, by the way. Now take a whole batch, say 100 training elements, right? Now just do the update thing for every element for that batch with respect to the same W, right? So for the simple perceptron, this was just plus or minus W. For this logistic thing, it was this more involved thing. Whatever you do, just do it for 100 training elements at once with respect to the same W, and then add all the up terms at once to W and obtain a new W. Yeah, this is really annoying. Yeah, and this is mainly a performance thing, so you might want to try it, but it also affects the precision. Yeah, you're getting a different W because you're not updating it after every sample, but just in batches. Okay, you can ask questions on the forum if something is not clear here. This was just a lot of ideas on which are also very practically relevant and used in practice to make the perceptron better.